This is the 26th lecture of the course MTH 204A for section B. So, today we will talk about Chinese remainder theorem first. So, recall that in the last lecture we have defined the coprimality of two ideals, the generalization of the coprimality of two integers in the setup of general rings. So, therefore, here let us start with a commutative ring which always possess unity and given a collection of ideals of R, then further assume that pairwise coprimal, coprime, that means for all I not equal to j, I plus I j is whole of R. So, this is the setup that we have. Now, with this we now state the Chinese remainder theorem. So, what does it say? So, given this collection of ideals, this intersection is an ideal, and on the other hand for each I we do have this. So, the Chinese remainder theorem says that these two are isomorphic, and in fact the following. So, okay, so in fact the isomorphism is also quite natural one, that is let me prove this directly. So, so from R to this product we have this very natural homomorphism, namely given by x goes to x plus I1 x plus ik. It is easy to see that this is a homomorphism, and what it is kernel? Kernel is intersection of all i's. So, now in view of the first isomorphism theorem, this will follow as soon as we can show this homomorphism is onto. Okay. So, as soon as we show that this homomorphism is onto, then by first isomorphism theorem we obtain the result. Now, the question is, why is this map going to be onto? So, therefore, what you have to see is what it means is the following, that given any a1 up to an, given a1 up to n where ai is in R, given in a1 up to an in R, we want to show that there exist x in R such that x minus ai is in ii, right. That is all we have to do, because this exactly this is same as x plus ii is a plus ii for every I. Okay. Now, you must be now you must have recognized why this is to be regarded as the generalization of the Chinese remainder theorem that we have seen for integers. Recall that the Chinese remainder theorem for integers that used to say the following, that given integers a1 up to ak, there is a x such that, right, this is what. So, each ni and nj or coprime. Okay. So, in view of the Chinese remainder theorem, what was obvious at that point was z modulo this n1 up to nkz because this is the intersection of these the principal ideal generated by AI NIs. Okay. So, the subjectivity of this subjectivity of the natural map follows from is basically the Chinese remainder theorem. So, keeping that analogy in mind, therefore, it is also legitimate to consider this as the Chinese remainder theorem in the general setup. Okay. So, now let me try to prove this. The proof is essentially, basically will mimic the proof for the mimic the proof of Chinese remainder theorem for integers in this setting. So, how to do it? Fix I, since I and ij are co-prime, therefore, there exists xi in ii and y and all right, maybe I should put okay. Here we do have this ai's I have used, so maybe I should use something else. So, okay, something maybe that is better, xi in I and yi in ij, such that xi plus yi is simply xi plus yi is 1. Okay. So, for each I we have this, remember yi belongs to, so fixing each I now for every j we do have this. Okay. I think better way is to index it by j, that is better. So, for a fixed y for each j this is what we have, therefore, the product must be 1, right, because this is the product of ones, and when we will simplify the left hand side, what we are going to obtain is the following, that recall that all xj's are in this ii. So, therefore, in any term whenever some xj belongs to that, it is going to be inside ii. So, therefore, what we obtain from here is xi plus this product of yj's equals to 1. Okay. So, xi is basically the all other terms, and it is clear that this belongs to ii. Okay. And then this quantity let us denote for the time being by capital yi. So, thus for each I we have xi plus yi equal to 1, forcing the ai xi plus ai yi ai. Okay. AIs are the given AIs. Now, you see that xi is in ii, right, xi is in ii. So, therefore, once we see both the sides modulo ii, what we will see is ai yi equal to ai plus ii. Maybe I can do it here. What we immediately see is ai yi is equals to, right, this is what is immediate. And also for the time being, for also if I not equal to j, then ai yi is plus ij is same as ij, right, because inside yi all y. So, inside yi this y capital yi, this small yj is there, and that makes this quantity inside capital Ij. So, now we know how to deal with the rest. simply it's almost ready. We will simply take the sum of YNs. Okay. So, when we will see, we will look at its coset modulo II. So, if I accept the ith term, all other terms will be 0 modulo II, and ith term will be AI modulo II, right. In view of this, therefore, we see that this exactly maps to this, shows the surjectivity of the natural map. So, you see this is nothing, the proof is nothing but the verbatim repetition of the proof for integers. Okay. So, this is how we prove the Chinese remainder theorem, and before we move on to something else, let me make one more remark. So, this the product of these ideals, this is certainly inside the intersection, right. This is certainly inside the intersection. I think I should I think everywhere it is to be replaced by k, right. Yeah. Okay. So, okay. Now, since they are pairwise co-prime, the collection is pairwise co-prime, from that it is not difficult to, we will argue that this implies in fact there will be an equality. How? This actually follows from, it is already in the proof of this Chinese remainder theorem, that if we take C to be inside each II, okay, then we have to show that it's inside, it's in the, so we have to show that it's in the, in this collection. Okay. So, maybe better idea is to first show it for 2 ideals, then eventually by induction we can do the rest. Okay, that's better. Or maybe let's see, I think directly I can do it if I find it. So, if C belongs to intersection, okay. Now, for each I we have, there we obtain some xi plus yi equal to 1. This implies cxi plus cyi is equals to C. Okay. Now, what is xi? Xi is basically, it's a so xi is basically the product of like except this, all this yi is the sum of all other terms. For example, all these terms are from okay, let me try to see it. Is it better if I do it for 2? All right. So, the we are supposed to show that this belongs to the intersection of this CIs. Okay. Therefore, C is in II, and this xi we have okay. So, yi. So, this is clearly inside, this is clearly inside this product, and basically we have to so what is xi? Some small xi's, and the terms where small xi's are not available, those terms are from others. Okay. So, therefore, is doesn't that follow immediately? Okay, maybe I should do it for 2, that is better, that is better. Then perhaps it will be rather more obvious. Suppose I and j are co-prime, I and j are co-prime, then I j should I intersection j. So, the one inclusion is clear. For the other direction, let C belongs to I intersection j, then since I and j are co-prime, so we have x plus y equal to 1 for some x in I and y in j, then this implies Cx plus Cy is equals to C. Now, so here you see that x was from I and C is from j, so therefore, this is a term in Ij, similarly this is a term in Ij, so therefore, the left hand side belongs to Ij, so is right hand side. So, for 2 ideals it is quite clear. Now, the rest is the following, now it is done actually. Now, for general collection I1 up to Ik, what we can do is the following, that using associativity I k minus 1 I k, right. So, the claim is if these are pairwise co-prime, then this ideal, that is the product of I1 up to Ik minus 1 and Ik, these 2 ideals are also pairwise co-prime, and that is exactly this argument taking I equal to k, right, taking I equal to k, exactly this is the argument, because at that time yi belongs to the product of other ideals. So, therefore, what we see is I1 up to Ik minus 1 intersection Ik, then you run the usual induction argument, because like now the collection has been reduced. So, if this is a collection of pairwise co-prime ideals, then their product is there just the intersection, and that proves the claim. Okay. So, thus in view of this, we can also rewrite Chinese remainder theorem as follows, that we can rewrite Chinese remainder theorem as isomorphic to okay. So, in case of pairwise co-prime ideals quotient by the product, now it breaks into product of the respective quotients. Okay. That is clear in view of this. So, and this form is rather this you must be able to immediately recognize that this is basically the generalization of that of something that we have seen earlier, namely if n1 up to nk are pairwise co-prime integers, then z modulo product of n1 up to nkz is isomorphic to z modulo nz direct sum z modulo n1 z direct sum z modulo n2 z. So, which I wrote a few minutes back, just to like show you that whatever you are doing is nothing very surprising. So, in case of integers, so if n1 up to nk are pairwise co-prime, so then you prove this, right. So, and in that case this collection used to be a pairwise co-prime collection. So, and so that their product is the ideal generated by n1 up to nk. So, now it is exactly in the most expected form. Anyway, I should now move on. The Chinese remainder theorem is done. Okay. Now, we will talk about prime and maximal ideals. So, let R be a ring, okay, non-trivial ring of course, because trivial ring we are not interested in the trivial ring. So, what we do is we consider the collection of all proper ideals. Here, as I said, unless otherwise said, is tacitly assume that all the ideals that we are considering are left ideals. Analogously, you can also talk about right ideals, or and then we have the notion for a general link of two-sided ideals, but we hardly will get into that. And in more often than not, we will have the ring commutative, so it does not matter actually. I is a proper ideal. Okay. So, this is a collection. On this collection, we impose a partial order. So, it is a relation. So, I will say I is less or equal to j if I is contained inside j. Okay. So, it is a collection of all proper ideals. Proper means I not equal to r. So, it is a collection of all proper ideals. Any maximal element of this collection is said to be a maximal ideal of R. So, what is the definition? So, I is said to be a maximal ideal if the following happens, that is, there is no proper ideal j such that I is strictly contained inside j, or in other words, if an ideal contains I, then contains I properly, then it must be whole of R. There is no other choice. Okay. So, this is the reason for calling it maximal is simply that it is the maximal of the element, it is a maximal element of this poset. When R is commutative, this is same as assume R is commutative, then I is a maximal ideal the R modulo I is a field. Okay. That is actually quite easy to see. For example, if you want to have a proof, let me prove this. So, I is a maximal ideal, so you have to prove it is a field. So, this is a ring, of course, in order to have, and this commutative ring, in order to have it is a field, then you have to show that every non-zero element must have an inverse. So, therefore, take a non-zero element from here, that means it is its representative will be x such that x does not belongs to I. Okay. Now, we consider this ideal. So, since x does not belongs to I, so this ideal contains I properly, so therefore, it has to be R. That forces that there exists A in I and there is some R in I and A in R such that this is 1, this is 1, and this immediately shows that Ax, like this immediately implies that A plus I times x plus I is 1 plus I. Okay. So, what have we shown? We have shown that what we have exactly shown that for every x in R not belonging to I, there is a element in the ring A such that 1 minus Ax belongs to I. That is all we have shown. This is the key point, rest is just immediate. Conversely, that if this is the case, again let me try to explain what we have proved here is for every x there exists A such that Ax minus 1 is in I. This is exactly the this is the crux. Okay, then let's do the second part of the proof. So, now this is given to be a field. So, again the argument would be very simple for every x. So, to choose take any x bin, right. So, since this is a field, we must have, there exists A such that for some A this must be 1, right. And expanding this, what you immediately see is A x minus 1 is basically belonging to I. So, so therefore, we see that I plus ideal generated by x must be whole of R. Okay. And that actually shows that I is maximal, because if there is some other ideal, containing I properly, then we must be able to choose an x inside that ideal outside I, such that this is an intermediate ideal, but this analysis shows that it has to be R. So, therefore, there cannot be any proper ideal. Okay. What I am saying is, it is enough to show that for every x this is R in order to show I is a maximal ideal, because if there is any ideal J containing I properly, then there will be, then if there is any such J, then for every x lying in J but outside I, this will be an ideal containing I properly, and now once it is guaranteed that this is going to be R, that forces J to be R, alright. So, this is very crucial. I would like to make one remark that if R is not assumed to be commutative, then this if R is not assumed to be commutative, then there will be a problem that we can, then this assertion actually does not hold. Okay. You can think of, you can construct examples. Okay. Let me now talk about some examples of maximal ideals. Okay, so we have for commutative cases, we have to look at its equivalent criteria in terms of quotient rings. Now, let me talk about some examples. What are the standard examples of maximal ideals? So, in case let R be Z and P be any prime, then P Z, it is a maximal ideal, because you see quotient will be simply Z modulo P Z, which is a field. Okay. Next example, well, when, as I have already told you that Z and polynomial ring over a field, they are very similar in nature. So, whenever we see something for Z, it is actually it is a common practice, or it is very natural to look at its corresponding version for polynomial rings over fields. So, like here let F be a field, we consider this polynomial ring, okay, and let Fx be an irreducible polynomial. So, by an irreducible polynomial, what I mean is that no such factorization exists such that both these have degree strictly less than. So, this is not possible. If so, we can't. So, if there is any factorization at all, then one of them must be constant. We call such polynomials irreducible polynomials, and the reason for calling it irreducible is quite obvious. It is exactly, it can be reduced in the sense of factorization. Okay. So, it is an irreducible polynomial, then like this, the principal ideal generated by this is again going to be a maximal ideal. Why? Because you can then, if you look at the quotient ring, Okay. If you look at the quotient ring, then the point is the following, that if you take any polynomial h here, then either this irreducible will divide that or they will be co-prime. That just follows exactly from the reducibility. So, either it is going to be co-prime or it will be dividing that. Okay. So, for if you take gx, so if f divide, take a polynomial gx here, if f divides, then that certainly the quotient ring this is going to be 0. Otherwise, since they are co-prime, you will have some g1, right, by Bezout's theorem, and then the rest is obvious. Reduce both sides modulo this ideal, you will see that g2 is going to be the inverse, the g2 modulo this principal ideal going to be the desired inverse. Sorry, g1 modulo the principal ideal generated by fx is going to be the inverse. Okay. Now, next example, I will quickly cite the examples because I have other things to talk about as well. So, the verifications I will be leaving to you most basically. So, let x be any non-empty set. We consider the set of all functions from x to f, where f is some field. Okay. And for any given x naught in x, define I x naught to be the set of all functions such that which vanishes at the point x naught. Okay. Check, so it is an exercise, this is a maximal ideal. This is a maximal ideal. All right, and similarly, if we replace all functions from x to f, if we just slightly change the setup, instead of just taking an arbitrary set, if we just take some topological space, and instead of all functions, if we just take its continuous functions on x, maybe real valued, complex valued, that does not matter, then we look at the corresponding version of Ix0, that is all continuous functions vanishing at that point, that will also be a maximal ideal of this ring of continuous functions. Okay. Proofs are exactly same. Okay. Now, next, ready up, boliye. Okay. So, now we will talk about other examples. The next example is, so let us take the ring to be Zx, the polynomial ring with coefficients from integers, and then let us take I to be the ideal generated by 2 and x. This is a maximal ideal. This is a maximal ideal. In fact, the quotient you can immediately see is going to be this field. You can further generalize this example. So, take P to be any prime, then ideal generated by P and x is going to be a maximal ideal of Zx. Okay. Similarly, you can what you can do is the following. Okay, so let's get into Zi. So, you can immediately check that the ID, if I is the principal ideal generated by 1 plus I, then certainly this is going to be a maximal ideal. You can, I am leaving these verifications to you. In fact, perhaps I will be doing a more general case shortly. Yeah, I think I should do the most general case. Then you will have an idea what is actually going on. So, suppose this is my ring and let me consider A and B two integers such that GCD of A and B is 1. Okay. Then I would like to know what happens to this quotient. Okay. A plus bi. So, I would like to identify this quotient. Okay. So, in fact, what we will be proving is this is going to be isomorphic to z modulo a square plus b square. This is what I will prove now. Then that will tell you that why this is a maximal ideal. In fact, something that we are going to see in much more generality. So, maybe I should do the proof here. So, from Z to R we consider the unique homomorphism, given that any Z, given that any ring R, from Z to R we have a unique homomorphism, right. So, we consider that homomorphism, and so therefore, how is this defined? This is nothing but defined as for positive integers n times, okay, and here it is nothing but basically n bar, right, because here in this ring identity is nothing but the coset of this. Okay. So, now look at kernel phi. So, kernel phi is going to be an ideal of Z. So, therefore, let us say it is generated by some k for k non-zero. It is generated by some k for k non-zero. Okay, yeah, for k non greater or equal to 0. Okay. So, therefore, you see that k must be a multiple of this quantity. So, okay, a multiple of this quantity may be here, maybe here I can drop this condition, maybe here I can drop this condition, rather let D to be the GCD of A and B, and we clear out the GCD. So, let D1 be A by D and A1 be A by D and B1 be B by D. So, therefore, I can now write A plus IB as, okay, and with that some U plus IV, right. Then like this is a non-negative, this is some integer. So, imaginary part of that is going to be 0. Since all these are integers, from that by a little bit manipulation you will see that this k must be of the form. So, I am just leaving this to you, because you just have to equate the imaginary part to 0, and that will tell you, since A1 and B1 are coprime, that will tell you that these are also multiples of U and V are also going to be multiples of AI, A1 and B1. So, this is what we are going to have, A1 square plus B1 square. Okay. So, all right. So, this is what we will get for some lambda greater or equal to 1. Now, at the same time we see that A plus, at the same time also we observe that A plus, so at the same time also we can observe the following, that A plus IB. So, I will just give you the sketch, because just a manipulation, and A minus IB is basically A square plus B square. This is also this also belongs to the ideal, right. This also belongs to the kernel, no? Yeah, this belongs to the kernel. So, since k is the generator of the ideal, from that it is quite clear, it follows that kernel phi is generated by a square plus b square, and so therefore, since it is a square plus b square, now we can use the first isomorphism theorem, provided we can show this homomorphism is onto. I think that part also I can leave it to you. Okay, maybe I should put it very clearly that this is what happens for any a and b, not necessarily they are co-prime, but when they will be co-prime, then this map is going to be onto. So, let me put it here. If GCD of a and b is 1, then this above map is going to be onto. How to show that? This again quite easy thing. So, we know that AU, there exists integers such that AU plus BV is going to be 1, right. So, that immediately shows that A plus IB into U plus IV is nothing but AU minus BV. Okay, maybe I should take V and U in this manner, plus I is, yeah. So, this is what we must have, and this is also so this belongs to I. Okay, I means this ideal, and from that it is quite easy to cook up. Maybe the inverse of maybe the negative of this is going to be the pre-image of I, right. So, once in the image I is there and also Z is there, then certainly this map is going to be onto. Okay. So, I have just briefly told you the strategy, leaving the details to you. So, the fact is that first, irrespective of GCD is 1 or not, we find out the kernel. Kernel we see that is going to be generated by this, and then we prove that if they are co-prime, then in the image, of course, integer points are there, and at the same time, so in the image, of course, cosets of integer points will always be there, and then with that coset of I is also there. So, there automatically the sub image will be the whole R. Okay. So, in view of this, now it is clear that why in the earlier case we have obtained a maximal ideal. All right. Next we should go ahead, since I do not have much time. So, as usual, that these are, as I said, that I have given you the outline of the argument, you can fill up the details. Okay. Then maybe I should give one or two more examples. Another example maybe I can give. So, you can simply compute 2x minus 3 x minus 10 is maximal in ZX, is maximal in ZX, and then of course, okay, what else? Then what else? What we can do is, okay, maybe I can get into the power series ring. So, let's consider the power series ring, okay, ring of formal power series, and let take I to be the principal ideal generated by this. So, is maximal if R is a field. Okay. In fact, this is if and only if actually, because the quotient is going to be isomorphic to R, given R a commutative ring, of course. Okay. What kind of other examples we can think of? Okay, another example that we can give is, In fact, I will leave it as an exercise here because the verifications are quite routine. So, as usual R is commutative ring, okay, and then we consider Rx, from Rx to R, sending each polynomial fx, we send it to f1. It is easy to, so this is just evaluation homomorphism. So, now prove that kernel is maximal if and only if R is a field. Okay. So, thus if R is a field, then we know, then we here we know this ideal is going to be maximal, and then the kernel of this evaluation, this is going to be maximal. Okay. So, that shows starting with a commutative ring, how to cook up some maximal ideals of power series ring or ring of polynomials. Okay. Now, I think now this is that I can move for prime ideals. Okay. So, as expected R be a ring. Right now I am not assuming it is commutative, and let P be an ideal. P be an ideal. The definition says P is said to be commutative if if the following happens, that is, whenever two ideals A and B, then that implies A is contained in P or B is contained in P. If whenever for all ideals A and B. So, let me again explain what it means. That is, first of all, it has to be a proper ideal such that whenever the product of two ideals will belong to P, will be contained inside P, then P must contain one of them. Okay. So, the reason for calling it a prime ideal is we are going to show that this is like this is actually the generalization of primality in the setup of rings. So, what you can expect that in the usual sense, if something is a prime, then ideal principal ideal generated by that is going to be a prime ideal. So, let me prove it here. This is we can record it as a theorem. So, it says that let P be a proper ideal of R satisfying the following. What is that? A B belongs to P implies A belongs to P or B belongs to P for every A B in R. Okay. This is the case. So, suppose I consider that an ideal proper ideal satisfies this property, then P is prime. Okay. From in view of that, you can immediately see that if in Z we consider a prime integer, then the ideal principal ideal generated by that, since this possesses this property, we will have that ideal is a prime ideal. Okay, that is clear in view of this. And also the converse holds, but however, for that we need P to be commutative. Note that if P is not commutative, then the converse does not hold. The converse does not hold if P is not commutative. Converse holds if P is commutative. Okay. Okay, so how to prove that? So, we have to show that P is prime. So, assume that for two ideals A and B, AB lies in A, and also assume that A is not contained inside P. We have to show P contains B. So, in view of this, you can immediately say that there exists A in P which is outside B. Okay. Now, for any B in B, we look at AB. So, AB is of course in okay. So, we look at AB. AB of course lies in P, right? AB has to lie in P, and this forces either A will be in P or B will be in P, but this does not happen. So, therefore, this has to happen. This shows that for every B, small b in B, B lies in P. So, therefore, B contains P. Straightforward proof. For the second part, what we have to do is the following, that now we assume P to be commutative. We have to prove that if AB belongs to P, then A belongs to B belongs to P. So, the natural choice is I will consider these two ideals when the A and B, when the ring is commutative, then actually we see that this is going to be contained inside AB, right. This is going to be contained inside AB, and since we if this holds, then this. So, therefore, since now we assume P to be prime, so either A is contained inside P or the ideal generated by B is contained inside P. That means either A is in P or B is in P. Okay. So, the proof of this is fairly obvious. So, note that. So, here we have defined both prime ideal and maximal ideal in case of any ring, not necessarily commutative, but when P is commutative. So, here the definition of a prime ideal is given in terms of ideal product of ideals, but when P is commutative, then we can safely simplify the defining criteria for product. I mean, we can simplify by product of elements. Okay. And this also tells us something. So, recall that for maximal ideals we have for commutative ring, in commutative rings an ideal is maximal if only if the quotient is field. So, here we have an analogous version. Here we do have an analogous version, assuming R is commutative, P is prime if and only if R modulo P is an integral domain. Okay, before that I should have told you what I mean by integral domain. So, let me put down the definition here. So, definition: a commutative ring, let R be a commutative ring, is said to be an integral domain if AB in 0 implies either A equal to 0 or B equal to 0. Okay. So, whenever a product vanishes, one of them must vanish. So, what are the examples? Z, Q, R, C. So, any subring of C is in an integral domain, then Zx, Qx, Rx, all polynomial rings. In fact, if R is an integral domain, then any polynomial ring over that is also going to be an integral domain. Clear? Because when you take the product of two polynomials, the top degree term will be, the coefficient of the top degree term is going to the product of the corresponding coefficients. From that it is clear that degree, if I take the product of two polynomials, the product degree of the product is basically the sum of their respective degrees. So, that is an integral domain, and of course, we have many more such other examples. So, let me just quickly put it here. Z, Q, R, C, Zi, Qi, polynomial rings. Okay. All these are examples of integral domain. Okay. So, if P is a prime ideal, then the quotient is going to be an integral domain. That is exactly clear, because if A bar B bar is 0 bar, that is A bar B bar lies in, that is A B is in P, then primality assures that one of them must be in P. So, therefore, A bar or B bar will be 0, similarly the converse. So, this proof is trivial. So, now I should give you some examples of prime ideals. Examples of prime ideals. So, if R is an integral domain, so what is an integral domain? Again, let me remind you, it is a commutative ring without commutative ring such that the product of two non-zero elements will again be non-zero. Okay. So, it is integral domain, then this is a prime ideal, this is obvious. Okay. So, one thing is quite clear that like R modulo P is an integral domain. So, if R modulo P is a field, then in particular it is going to be integral domain, right, because like you see in this property is automatically there in every field, right. So, therefore, every field is automatically integral domain. So, if R modulo P is a field, then certainly it is going to be an integral domain. What does that yield? It yields that in a commutative ring, of course. Let us stick to the commutative setup. In a commutative ring, we do have every maximal ideal is going to be a prime ideal, right. So, in particular here, yeah. So, therefore, we must say that, let us take our commutative ring, every maximal ideal is prime. However, the converse is not true. Converse is not true. Example. So, a very easy example is if R is an integral domain which is not a field. For example, if you take the polynomial ring, it is an integral domain, but it is not a field, then this trivial ideal is going to be a prime ideal which is not maximal, right. We will also give another example. Like which I was just telling that another example for this is of course, one example I just told you that if R is an integral domain which is not field, then this trivial ideal is going to be a prime ideal which is not maximal. And next thing that I am going to, yeah, so another example for this is very simple, that is in this is going to be a prime ideal in ZX, but not maximal. Okay. Because the quotient is going to be isomorphic to Z, which is not a field. Okay. Not a field, then okay. So, only a few minutes I am left with. So, there I would like to say two things. One is basically I would like to leave an exercise. So, as usual, let R be a commutative ring and I be an ideal proper ideal, then we define Ix to be all the polynomials whose coefficients also come from the ideal I. Okay. So, remember that this is not any ring. Okay. So, this is just a collection of all polynomials whose coefficients are also coming from that ideal. It is easy to see Ix, you can immediately see Ix is an ideal in Rx. So, I am leaving this as exercise. The second thing is this is which follows from something what we have done earlier, namely reduction. Okay. So, this immediately, so this is what I am leaving for the verification to you. So, this immediately shows that if I is a prime ideal, so this shows corollary I is prime, then Ix is also prime. Okay. I am leaving, but however, also should let me make you remark that does not hold for maximal ideal. That is, if I is a maximal ideal, it need not be true that Ix is a maximal ideal of Rx. Hold for maximal ideals. Okay. All right. Now, I will be finishing this lecture by a small thing. So, namely by the existence of maximal ideals for any commutative ring. So, now onwards, unless for mostly we will be concentrating on in the setup of commutative rings. So, maybe this is recorded as a theorem. I will just briefly give you the sketch. So, again R is a commutative ring. Okay. As let us consider the ideal to begin with, the collection I is a proper ideal. Okay. So, if R is a field, then certainly this is going to be a maximal ideal. So, our purpose is served, and if R is not a field, then there exists, I will just finish in a moment, then there exists for Rx is not, if R is not a field, then S is non-empty. Okay. So, then recall that on S we have the partial order relation. Okay. So, on this non-empty poset, applying John's lemma, I am leaving the details to you because you know John's lemma and how to use that. So, using John's lemma, we can assure that there is a maximal element. So, that shows that given any commutative ring, there is always a maximal ideal. Okay. So, with that I finish this lecture.